right? Angular velocity is equal to linear velocity times 1 over r. And then also, if we switch things around, the linear velocity is equal to the angular velocity times r. We had one important rule there, and that is that angular velocity must be in radians when we use it in the equation. Otherwise, the units aren't going to cancel out nicely. Okay? That becomes a little bit more relevant today. All right, then on last Tuesday, we talked about concentric circle systems. So we used that merry-go-round example. And we said, okay, anywhere on the merry-go-round, the angular velocity is the same. You had to turn through the same angle, regardless of where you were standing on the merry-go-round. But depending on how far from the center of the merry-go-round you were, your linear velocity changed. And so we found that the angular velocity was constant on that concentric circle system, but the linear velocity depended on how far from the center you were, that value of r in those equations. All right, the greater the radius, the greater the linear velocity. The farther away from the center of that merry-go-round, the faster you were moving. And then I told you guys on Tuesday that these rules would change depending on the system. So today we're going to look at a different system. Tuesday, we talked about concentric circle systems. Those were circles that had the same center. Today, we're going to look at something else. We're going to look at pulley and gear systems. So this is what those look like, right? Gears with the teeth that move each other, or gears that are attached to belts or chains or pulleys, things like that. So that's the system we're going to focus on today. And today, instead of the merry-go-round example, I'm going to use the example of bike sprockets. So if you've ever seen a bike, hopefully you have, that's what we're using today as our example instead of the merry-go-round. Okay? So here's what I'm going to do. I've drawn a picture, exaggerated a little bit, but hopefully we can tell that gear A and gear B are different sizes, right? Yeah. All right, and then we have a bike chain that goes around these two gears, right? And as, the cyclist is pedaling the bike, the chain is moving around these gears, and that's what's getting the wheels to turn so that the bike moves. And we're going to look at how the chain moves. That's kind of our goal today. It's to see how the chain moves and then see how that relates to linear and angular velocity. Okay, so I made up a number. Imagine that the chain is moving at 2.28 centimeters per second. It really is an arbitrary value. I probably could have picked a nicer number for the point of this example. But let's say, for the sake of this problem, right, to get from this point to this point, we've moved 2.28 centimeters in 1 second. But what has to be true of this entire system then is if I move 2.28 centimeters here in 1 second, we must also move 2.28 centimeters down here in 1 second, or 2.28 centimeters over here in 1 second, or 2.28 centimeters over here in 1 second. That chain has to move the same speed everywhere in the system, otherwise we get a problem, right? Imagine if the chain of your bicycle is moving at different speeds in different places. That's when you get the chain popping off the gears, and then an accident, right? And it hurts when you fall. So in order for all of this system to be working properly, that chain needs to move at the same speed, regardless of where we are in the system. Right? So that gets us to our first of two rules for a pulley gear system. The first rule is that the linear velocity has to be the same everywhere. The chain has to move at the same speed, no matter the location, so the linear velocity must be the same on a pulley and gear system. Maybe write that down. The linear velocity has to be the same on a pulley and gear system. Remember that on a concentric circle system, it was different. So the system matters, especially tomorrow when I start combining them. All right, but here's what happens. That 2.28 centimeters that the gear is going to turn that chain is going to look different on the different sized gears. 2.28 centimeters around gear A is more of the circumference of gear A than it is of gear B because gear A is smaller. So I've highlighted the angle that they're turning through. In order to move that chain 2.28 centimeters, gear B only has to turn through this angle. But to move the same length of chain in the same amount of time, gear A has to turn through a larger angle. So in a Pulley and gear system, linear velocity is the same. Angular velocity is going to differ. All right, our 2 rules for today. We're really focusing on this. I did the math for you guys, but we're focusing here. Angular velocity depends on the radius today, whereas the linear velocity is constant on the system. I'm going to make like a quotation or stars here where the system is connected. And we'll talk about that when we get to the examples today. But where those gears are connected to one another, which is typically on the outside. Okay. All right. First example of the day. Here we go. On page 5, at the top, we've got this gear problem. We have 3 gears. A large gear of diameter 100 inches rotates at 60 revolutions per minute. Well, I'm going to mark this on the diagram, but instead of writing just the information we were given from the problem, I'm only going to write the information that's actually useful. So we don't use diameters in any of the equations for angular or linear velocity. We use the value of the radius. So I'm going to write 50 inches here, just so when I reference my diagram, I'm using the right numbers. We are also told that this gear rotates at 60 revolutions per minute. Okay, I know it's Monday. It's been a long day. You're also back from break. But you guys need to tell me, 60 revolutions per minute, angular or linear velocity? What is it? Angular, yes. Revolutions per minute, angular. Just something to note, right? Just think about what information you're given first, and sometimes that can be really helpful in how you answer the question. Okay, this large gear drives a small gear of diameter 32 inches. So that has a diameter of 32 inches, which means that its radius is 16 inches. And the medium gear has a diameter of 68 inches, which means the medium gear has a radius of 34 inches. And the first question that's up is how many degrees per second is the large gear turning? Now, how many degrees per second is our large gear turning? Degrees per second is angular velocity. But that 60 revolutions per minute is already angular velocity. So this is why I say think about what you're given first. We already have angular velocity, which means I don't need one of those 2 equations. We just need dimensional analysis to help us turn revolutions per minute into degrees per second. So I'm going to start with what we have, which is 60 revolutions per minute. And we're just trying to get those revolutions into degrees and the minutes into seconds. So I'm going to start with revolutions to degrees. What do I know? Well, 360 degrees is 1 revolution. Okay, revolutions cancel. Now I have degrees over minutes, but I'm looking for degrees over seconds. So I need to turn the minutes into seconds last. All right, 1 minute is 60 seconds. And again, I'm being thoughtful about where I place my units to make sure that there's something on the top and the bottom that cancel. And then you multiply. Luckily for us, the 60 is on the top and the bottom cancel. So we're just left with 360 degrees per second. That's it. Okay, I'm going to note, because I got to keep track of these things. It's a lot easier if I just mark it now. This is still the angular velocity of our large gear. Remember, in our new system today, angular velocity is going to be different for each of those gears because their sizes are different. All right, next up. How many radians per minute is the large gear turning? Well, again, radians per minute is also in angular velocity. So again, we don't need to use an equation. We're not solving for anything. We're just converting from units to other units. You have 2 options here, you guys. You can use 360 degrees per second, or you can use 60 revolutions per minute. Doesn't matter. One of them makes your life a little bit more easy. I'm going to use 60 revolutions per minute because revolutions per minute is already in minutes, so I don't have to convert. I have to convert less is the where I'm going there. All right, so 60 revolutions per 1 minute. In order to turn that into radians per minute, I'm just going to turn revolutions into radians. All right, 2 pi radians is 1 full revolution. I had a question in my last period, which was revolutions and rotations. What's the difference? They're the same thing. Okay, so revolutions and rotations are the same. All right, what happens? The revolutions cancel. We're left with radians per minute, which is what we want. And that looks like 120 pi radians per minute. Again, that is still the angular velocity of the large gear. We have 3 angular velocity values for the large gear. Same piece of information, just different units. Okay, so then finally we get to part C, which is actually going to require us to solve for something using the equations that we've got. What is the linear velocity at the rim of the large gear? So linear velocity, we've got an equation for that. That is angular velocity times r. Now, when we use angular velocity in this equation, you only get one option here. Of the 3, we have to use the one in radians. So you have to use the correct one, otherwise you're not going to get the right answer. That's really the only mistake people make on this test, right? Or they don't look at the units that their final answer needs to be in. But like most people, by the time we take the test next week, have the equations down and things like that. Okay, 120 pi radians per minute, and then times the value of r, the radius, which is 50 inches. And then don't forget, you guys, when we're working with r, you have those like weird invisible units that show up and disappear as needed. Okay, Amelia, question?
Do you have to do radians because you're working with the radius?
Yes, you have to do radians because this is where it cancels. Okay. That's a good question, yeah. That's why. Okay, 12 times 5 is 60 times, add 2 more zeros. What are we at? 6,000 pi inches per minute. There's our linear velocity. Question?
Are we like ever going to use diameter in this unit, or should we just like
No, that's why I say, if I give you diameter, just write the radius so that you don't make the mistake of using it. All right, that is the linear velocity of our large gear at the rim, you guys. That's what's really important here. So imagine we have a belt that's connecting all of these gears together. That belt only runs around the rim of those gears. So that's why that's really important. The linear velocity is the same everywhere where the system is connected. The linear velocity on the middle of this large gear is still different, okay, than the outside, because we still have to follow concentric circle rules as well. So it's only the same where the system is connected. So kind of keep that in mind. But there's our linear velocity at the rim of the large gear. So then the next question is, what is the linear velocity at the rim of the small gear? But the linear velocity is the same everywhere on a concentric circle, Pulley and gear system. So still 6,000 pi inches per minute is our linear velocity on the small gear as well. It's the same everywhere. Okay, so then we go into how many radians per minute is the medium gear turning then? Well, radians per minute, I'm still asking for angular velocity here. I need to know what the angular velocity of the medium gear is. Now, it's going to be different because it's a different circle than the large gear. So we have to use the equation. Angular velocity is linear velocity times 1 over r. We have the linear velocity of the medium gear. It's the same as the small and the large gears. 6,000 pi inches per minute. And we're going to multiply that by 1 over r. What is the radius of the medium gear? Somebody tell me. 34. Thank you. All right, inches cancel. We're left with radians per minute. 6,000 pi divided by 34. Do that on your calculator. 6,000 divisible by 34. Nicely. Without a decimal. No. Okay, great. So then 3,000 pi over 17. 3,000 pi radians every 17 minutes is how we're going to express that angular velocity. And then the last question for this problem, how many degrees per minute is the small gear turning? Well, degrees per minute is also angular velocity, so I need the angular velocity equation. Still v times 1 over r. And the angular velocity is still going to use the same linear velocity for the whole system. So 6,000 pi inches per minute. And this time times 1 over the radius of the small gear, which I think is 16 inches. Okay, but here's the problem on this one. When I go to give an answer here, my units currently are radians per minute, because that's angular velocity when it comes out of this equation. I want my final answer though in degrees per minute. So I'm going to go one step further here, and I'm going to turn the radians into degrees, using what we know about the relationship between radians and degrees. 180 degrees is pi radians. And then that allows me to cancel these radians out so that I get degrees over minutes. Okay, the pi's cancel. And then 6,000 times 180 divided by 16. I don't know what that is off the top of my head. What is it? 6,000? 67,000 what? 500. Thank you. 67,500 degrees per minute is your answer on that one. That's a lot of degrees per minute. Okay. Next example, here's what we're going to do. I want you guys to try A, B, and C with the person sitting next to you, but I'm going to give you a couple of hints here, because B is the trickiest one. But then I'm going to do D with you, which is also tricky. Read the problem, because I've given you one measure in a diameter and one in a radius. So just be careful on that. And then find the information for A, B, and C. I will put the answer up in just a minute with the worked out steps, but say hello to the person sitting next to you, happy Monday, and then get started on A, B, and C. Do that now. So before I get to D, let's talk about A, B, and C here, okay? So the first thing for part A, you guys, you already have the angular velocity of the small gear. You have it in just different units. 200 rotations per second, that's already angular velocity. So for part A, no need to apply any of the equations. We just need to turn rotations per second into, what are we looking for? Degrees per minute. So 4,320,000 degrees per minute. That's our final answer on that one. And I'm just turning the rotations into degrees and the seconds into minutes here. So then when we get to part B, you might have done this differently if you did it, okay? You guys definitely did it in the back differently. I used 200 rotations per second and then converted that into radians. This whole thing in the brackets together then, that gets us the angular velocity that we're allowed to use in the equation. Remember, we're not allowed to use angular velocity if it's not in radians. So what I did in the brackets here is I took my 200 rotations per second, which is angular velocity, but I turned it into radians so that it will work out in this equation. Then I multiplied it by the radius, because that's the equation that we're told to use. And I get this answer. I get 1,600 pi nanometers per second. But if you guys used the 4,320,000 degrees per minute, your answer per minute should be 96,000 pi nanometers per minute. Okay? So either one, perfectly acceptable, because I didn't tell you what units I wanted your final answer in. And then we get to C, which is where I said leave off, because I'm going to help you guys with D. But C asks what the linear velocity of the large pulley is at the rim. Well, remember that the linear velocity is the same anywhere in the connected system. So if it is 1,600 pi nanometers per second on the small pulley, it's going to be the same on the large pulley. Okay? Or 96,000 pi nanometers per minute. But then this is where it gets even trickier, which I think B was actually kind of tricky because you also had to convert to radians there. But D is a kind of different question here. D is asking, find the angular velocity at the center of the large pulley. Okay, angular velocity. Here's what I'm going to do. I'm just going to write the equation for angular velocity. It is linear velocity times 1 over r. Now here's the question. When we're sitting at the center of a circle, what is the value of r?
0.
0. So when I plug 0 in here, what do I get? Undefined. But there's a problem with that. Because I know that this circle, this gear, has to have an angular velocity. If it's turning, it has an angular velocity no matter where we are on that gear. So it can't be undefined. So what we have to do is approach this a little bit differently. When we're finding the angular velocity, remember that on a concentric circle system, like on its own, if we were to just look at this gear by itself, no matter where we're sitting on the gear, the angular velocity is the same. What we're given, the only thing we know about the two gears is that the linear velocity on the outer rim of those gears is the same. So in order for us to find the angular velocity of the large pulley, we're going to calculate the angular velocity of the large pulley at the rim, because that's where the linear velocity is that we have. And then what we know about the same concentric circle system is that the angular velocity is the same everywhere. So if we find the angular velocity at the rim, it's the same at the center as well. So we have to do it. All right, so our linear velocity is, take your pick, one of the two options from C. I'm going to go with the seconds. 1,600 pi nanometers per second times 1 over the radius of the large pulley, which was 46. Remember, when we're working with the radius, the radian unit kind of comes and goes. Nanometers cancel. And that leaves us with radians per second, which is great. That's what we want. And then we got to do some math. 1,600 divided by 46. Is that a thing? I don't think so. Great. So 800 pi radians per 23 seconds is our final answer there. And then the last thing is, how many revolutions per minute is the large pulley turning? Now, revolutions per minute, again, is angular velocity. We already found the angular velocity. We just did that in part D. So we're going to take that 800 pi radians per 23 seconds. We're not going to plug it into any equation. We're just going to apply dimensional analysis to turn the radians per seconds into revolutions per minute. Okay, so I'm going to do that quickly. Radians to revolutions. 1 revolution is 2 pi radians, and then 60 seconds is 1 minute. The radians cancel, the seconds cancel, we're left with revolutions per minute, which is what we want. Okay, so what happens there? We get, the pi's go away, 400 times 60, is that 24,000 over 23. Like that. Somebody with a calculator, tell me if you got the same thing. Yeah, thank you. Okay. Turn the page. One more thing. We're going to look at a truck. All right, last example here. We've got a truck. It's a really big truck because the front wheels of the truck are 5 feet in diameter. That's huge, by the way. Okay, so they are turning also at 225 revolutions per minute. And we are asked first to figure out what the truck's speed is. Now, speed, that's linear velocity. Also, how do we measure the speed of a vehicle? Miles per hour, which means that's what our final answer needs to be in terms of, okay? Miles per hour there, which means we're going to have a decimal value for our answer because otherwise it gets way too complicated. All right, we need linear velocity here, which is angular velocity times the radius of whatever the wheel is. So we go in. Now, angular velocity, we have it as 225 revolutions per minute, which is a problem because it's not in radians. So when I actually go to plug in our angular velocity that we're given, I need to do a conversion into radians before I can actually finish the problem. So 225 revolutions per minute. I'm going to multiply that by the conversion from revolutions into radians. So 2 pi radians is 1 full revolution. And that together makes up the angular velocity for this problem. Then I'm going to multiply by the radius. Now, if the wheel is 5 feet in diameter, the radius is 2.5 feet. And then remember, we're working with a radius here, which means we have that invisible unit. And then if I take a look at the units that cancel, the revolutions cancel, the radians cancel, and now I'm left with feet per minute. But we don't want feet per minute, we want miles per hour. So I'm going to continue to convert until I have the right units. So I'm first going to convert feet to miles. There are 5,280 feet in 1 mile. The feet cancel now. So now I'm left with miles over minutes, so I need to convert the minutes to hours. There are 60 minutes in 1 hour. And then the minutes cancel. And now we have miles over hour. You definitely want a calculator for that. Do that. See what you get. Don't forget the pi, you guys. People were forgetting the pi in their calculations earlier, and then they were getting the wrong answer. 225 times 2 times pi times 2.5 times 60. Divide that by 5,280. You should be getting 40.16 miles per hour. That's how fast your truck is going. Okay. Save that decimal, all right? Because we're going to come back to that, like the long decimal, the 0.162400608. I'm going to use that in part C, but let's talk about part B really quickly. The rear wheels have a diameter of 3 feet. What is the linear velocity on a point on the treads? Well, what do we know about linear velocity? It's the same everywhere in a connected system. All of the wheels are touching the ground. That's what connects them. Also that they're attached to the car. So the linear velocity has to be the same everywhere. Another way we could think about it is this. If you're driving a car and all of the wheels of your car are moving at a different speed, you're going to have some problems. Okay? All the wheels have to turn at the same speed. Otherwise, you got issues. You got to travel at the same speed. Okay, so then the last piece here, what is the angular velocity of the rear wheels in revolutions per minute? Angular velocity is linear velocity times 1 over r. So I'm going to use that 40.16 miles per hour, but I'm going to use the full decimal when I go to calculate this in my calculator. Times 1 over r, the radius of the smaller wheels is 1.5 feet. I'm working with the radius here, which is where the radians pop up again. And then we need it in revolutions per minute. Right now, as it stands, actually nothing is canceling, so I've got to do some work here. Feet and miles, they don't cancel each other out, so I've got to turn the feet into miles before I can finish this problem. 5,280 feet are in 1 mile. And then we see the feet cancel with the top and the bottom feet, and the miles cancel as well. Great, so what do we have left? Now we have radians over hours, but we need revolutions per minute. So I'm going to turn the radians into revolutions. 1 revolution is 2 pi radians. And then the last thing I need instead of hours is minutes. So 1 hour is 60 minutes. Type that into your calculator. If you did this correctly and you use the full decimal, you should get a nice number. .375 revolutions per minute is your final answer there. Okay. I'm going to come around and stamp the homework that was due today. So pull that piece of paper out and your stamp sheet. Grab a brand new piece of paper, and you guys are going to start in on the problems right underneath example number 3. So you guys are doing 1 through 8 for homework on a separate piece of paper. Diagrams need to be shown. I'm going to put the answer key up so you guys have that while you're working through this. All right, so the answer key looks like this. And then let me know if you've got any questions as I come around and stamp your homework today. All right, you guys, the last lecture of the semester is done. Yay. All right, there you go.